Welcome to a journey through the heart of cosmic balance. In this video, we'll explore the concepts of cosmological self-equilibrium, CSE, and the cosmological equilibrium constant, CEC. These ideas propose that the universe and even the multiverse are not just random or chaotic, but are governed by deep principles of balance and self-regulation. Whether you're a science enthusiast, a philosopher, or just curious about how everything connects, this series will guide you from the foundations of equilibrium to the cutting edge of symbolic and mathematical representation. Let's begin by understanding what it means for the cosmos to be in equilibrium and why this matters for everything that exists. Cosmological self-equilibrium, or CSE, is the principle that the universe is an actively self-regulating system. Rather than being passive, the cosmos constantly adjusts itself, balancing expansive and contractive forces across all scales. Imagine gravity, dark energy, and quantum fluctuations all interacting in a cosmic dance, ensuring that the universe neither collapses nor flies apart uncontrollably. This dynamic balance is not static. It evolves as the universe changes, absorbing disturbances and correcting itself to maintain order. CSE suggests that the universe is like a living organism, always seeking harmony within itself. Cosmological Equilibrium Constant, or CEC, is a theoretical metric that quantifies the universe's balance. Think of it as a cosmic ratio, the amount of order versus disorder or balance versus imbalance at any given moment. When CEC equals 1, it means the universe is in perfect equilibrium. This constant is not just a number, it's a guiding principle that helps us understand how the universe maintains its structure, from the smallest particles to the largest galaxies. CEC is the output of the self-balancing process described by CSE. Make these ideas more intuitive, we use symbols. The asterisk stands for everything or anything, all possible states, entities, or realities across the multiverse. In contrast, the empty set symbol O* represents absolute nothingness, the primordial void from which all existence emerges. This duality for totality and O* for nothingness forms the backbone of our symbolic framework. It allows us to express the journey from nothing to everything and the constant interplay between existence and non-existence. The heart of CSE is a simple but profound equation. CSE asterisk equals some sign EX IX, right arrow 0 as X approaches asterisk. Here EX represents external expansive forces like entropy or cosmic inflation, while stands for internal contractive forces such as gravity or coherence. We sum over all X, meaning all points, entities, or states in existence. The net difference between expansion and contraction trends toward zero. This is the mathematical expression of universal balance. EC is defined as the ratio of balanced states to imbalanced states across everything. CEC equals sigma balanced states / sigma imbalanced states. When this ratio approaches 1, the system is in ideal equilibrium. In other words, the universe is always striving to keep this ratio as close to 1 as possible, ensuring that chaos and order are perfectly matched. This ratio can be applied not just to our universe, but to any system, including the multiverse. CSE and CEC are not just abstract ideas, they bridge the gap between philosophy and physics. Philosophically, they echo ancient ideas like yin and yang or the Taoist balance of opposites. Physically, they connect to modern cosmology, where the interplay of gravity and dark energy shapes the universe's fate. By uniting these perspectives, CSE and CEC offer a holistic view of reality, where science and metaphysics meet. But if our universe is just one of many, the multiverse theory suggests that countless universes exist, each with its own laws and constants. In this expanded view, both CSE and CEC apply not just within a single universe, but across the entire multiverse. Each universe seeks its own equilibrium, but there are also interuniversal interactions, gravitational, quantum, or otherwise, that influence the balance of the whole multiverse. The multiverse, the CEC, becomes a sum over all universes. C multi equals sigma CIFUIUJ, where CI is the CEC of the ITH universe and FUIUJ represents the interaction between universes. This could include gravitational pull, quantum entanglement, or other forms of influence. The multiversal CEC captures the collective balance, showing how universes can affect each other's equilibrium. How do universes interact? Two main possibilities are quantum entanglement and gravitational influence. Quantum entanglement could link universes at a fundamental level, allowing changes in one to affect another instantly. Gravitational forces, especially in higher dimensional models, might allow universes to pull on each other, altering their expansion or contraction. These interactions are modeled mathematically in the multiversal CEC equation. Symbolize cosmological equilibrium and its manifestation, we use omega. Here E stands for equilibrium and omega represents the totality of existence. Everything that exists is a manifestation of this equilibrium. Symbolically, for all X and asterisk is a subset of omega. This means every entity, event, or universe is an expression of the underlying cosmic balance. Mathematical heart of CSE is an integral. CSET equals integral EXT IXT dx over all X and asterisk. Here X represents any point or entity in existence and dx is an infinitesimal slice of reality. EXT and IXT are the expansive and contractive energies at each point in time. The goal is for the total sum to approach zero, meaning perfect balance. CEC is not just a static ratio. It can be expressed as a function of CSE. Specifically, sec t equals 1 / CSET plus epsilon, where epsilon is a small constant to avoid division by zero. As the net difference between expansion and contraction, CSE, approaches zero, CEC approaches infinity, indicating perfect equilibrium. This ties the dynamic process of balancing directly to the measurable constant of equilibrium. CEC can also be understood in terms of entropy. In this view, sec t equals s neg t slash s pos t, where s neg is negentropy order-forming processes and s pos is entropy disorder. This ratio shows that even in a universe full of chaos, there are always self-organizing processes at work, maintaining the overall balance. In the multiverse, each universe has its own balance and imbalance metrics. The multiversal CEC is the sum of all balanced states across universes divided by the sum of all imbalanced states. This treats the multiverse as a statistical ensemble, giving a collective measure of equilibrium that transcends individual universes. Let's clarify the symbols used throughout this framework. The asterisk means everything or anything. O stroke is absolute nothingness. EXT is expansive energy at point x and time TIXT is integrative energy. Means element of, so XX means belongs to set X means subset of and means for all. These notations help us express complex ideas with elegant simplicity. One profound idea is that CEC is always one. This means the cosmos maintains perfect dynamic balance at all times. No matter how chaotic or orderly things seem locally, the total sum of expansive and contractive forces always cancels out. This is like a cosmic seesaw that never tips no matter what happens. It's a foundational postulate that underpins the entire framework. Can we predict the next state of things if CEC is always one? Not exactly. CEC acts as a constraint, not a calculator. It ensures that whatever happens, the overall balance is preserved. Locally, systems may fluctuate, but globally, the cosmos compensates. This is similar to conservation laws in physics. Energy may move around, but the total remains constant. How can we use CEC equals 1 in deterministic modeling? By defining a local system and tracking its expansive and integrative energies, we can constrain the range of possible outcomes. If expansion exceeds integration, the system moves toward transformation. If integration dominates, it stabilizes. CEC doesn't predict exact outcomes, but it narrows the possibilities to those that fit within the equilibrium envelope. To predict future states more precisely, we need more data, both over time and across different conditions. By increasing the amount of training data, models can capture more patterns and generalize better. This is true whether we're modeling physical systems, economies, or even emotional states. The more data we have, the more accurately we can simulate the interplay of expansion and integration. Simulating a system with CEC1 involves modeling feedback loops. If expansive forces grow too large, integrative forces increase to absorb the excess and vice versa. This self-correcting mechanism ensures that the system never strays too far from equilibrium. Feedback loops are central to maintaining balance, whether in nature, society, or the cosmos. Stochastic elements introduce randomness or uncertainty into a system. Unlike deterministic models, where outcomes are fully predictable, stochastic models account for unpredictable fluctuations, like weather, stock prices, or quantum events. In CEC and CSE, stochastic noise represents real-world disturbances that challenge balance but don't break it. These random elements make simulations more realistic and dynamic. Simulate a CEC equals 1 system. Start by defining state variables for expansion and integration at every point in time. Use differential equations to model their interactions, discretize the system for computation, and introduce feedback loops. Add stochastic terms to reflect real-world unpredictability. Run the simulation over time, monitoring how the system maintains balance despite disturbances. After running the simulation, analyze the results by plotting expansion and integration over time. Look for cycles, tipping points, and periods of instability. Check that the overall balance is preserved even as local fluctuations occur. Adjust parameters and improve the model by increasing data and refining the feedback functions. Let's apply these ideas to a simple economic system. Expansive forces might include investment and innovation, while integrative forces are resource limits and regulations. By simulating how these interact over time, we can see how the system maintains equilibrium even as it faces shocks or changes. This approach can be extended to any complex system. Here's a quick reference for the symbols used. Means element of, means subset of, means for all is everything, O stroke is nothing, EXT is expansive energy, IXT is integrative energy, and DX is an infinitesimal element. These symbols make it easier to express complex relationships in a compact form. Symbol means subset of or equal to, indicating that all elements of one set are contained in another. The symbol is the universal quantifier, meaning for all or applies to every element. These are essential for expressing relationships like all things are manifestations of equilibrium, or for every point in existence, balance is maintained. Journey from absolute nothingness, O stroke, to everything is at the core of cosmological equilibrium. The universe and possibly the multiverse emerges from the void, manifesting as a dynamic interplay of expansive and integrative forces. This process is captured in the equations and symbols we've discussed, showing how balance arises from the most fundamental level. The multiversal framework, universes are not isolated. Each universe's equilibrium can influence others, leading to cosmic interdependence. This means that the fate of one universe may be tied to the balance of the whole multiverse. The CEC and CSE equations are extended to account for these interuniversal interactions, creating a grand tapestry of balance. Philosophical implications of CSE and CEC are profound. They suggest that existence is not random but guided by a universal drive toward balance. This echoes ancient wisdom and modern science alike, offering a unified view where chaos and order, creation and destruction are all part of a self-regulating whole. If you're inspired to share your own ideas about CSE and CEC, there are many ways to publish. Platforms like Zenodo, Medium, and RZiv allow anyone from scientists to enthusiasts to share their work with the world. You don't need formal credentials. Clarity, structure, and openness are what matter most. Your intuition and systems thinking are valuable contributions to the ongoing exploration of cosmic balance. Help visualize how CSE and CEC link. Imagine a diagram where the void O-stroke gives rise to everything, which is governed by the equilibrium principle omega. CSE describes the dynamic balancing process while CEC measures the degree of balance. In the multiverse, these principles extend outward, connecting all universes in a web of interdependence. Let's revisit the core CSE equation. CSE asterisk equals sum sin EX IX right arrow 0. In integral form, CSE t equals integral EX t IX t dx over all x and asterisk. This models the universe as a continuous feedback loop, where the divergence between expansion and contraction trends toward zero over time. In the multiverse, this becomes a sum over all universes, each contributing to the global balance. EC is defined as sec t equals bt ut, where bt is the measure of balance and ut is the measure of imbalance at time t in the ideal case. As t approaches infinity, CEC approaches 1. This ratio can also be expressed as a function of CSE, sec t equals 1 slash CSE t plus epsilon. In the multiverse, CEC is aggregated across all universes, giving a collective measure of equilibrium. CSE equation can be written as a differential equation. dCSE t slash dt equals integral EXT IXT dx for all x and asterisk. This models the rate of change of equilibrium over time. The objective is for CSE t to approach zero as t goes to infinity, representing a self-regulating universe. In thermodynamic terms, CEC can be expressed as the ratio of negentropy order-forming processes to entropy disorder. This highlights the interplay between chaos and order, showing that even in a universe full of randomness, there are always organizing forces at work. In the multiverse, feedback mechanisms operate across universes. If one universe becomes too chaotic, others may compensate, maintaining the overall balance. These feedback loops are modeled in the multiversal CEC equations, reflecting the interconnectedness of all realities. Imagine two universes with different dark energy densities. One expands rapidly, the other more slowly. Their interaction through gravity or quantum entanglement can cause each to adjust its expansion rate, maintaining the multiversal equilibrium. This scenario is modeled mathematically in the multiversal CEC framework. Make simulations more realistic. Stochastic elements, random fluctuations, are added to the equations. This reflects the unpredictability of real-world systems, from quantum events to social dynamics. By including stochastic noise, models can better capture the dynamic, ever-changing nature of equilibrium. Let's recap the key symbols. Means everything. O-stroke is nothing. EXT is expansion. IXT is integration. Is element of. Is subset of. Is for all. And dx is an infinitesimal element. These notations are the language of equilibrium, helping us express the deepest truths about the cosmos. CSE and CEC are more than theoretical constructs. They offer practical tools for understanding and modeling complex systems. Whether you're studying cosmology, economics, or personal growth, these principles can guide you in seeking balance, predicting change, and appreciating the interconnectedness of all things. You don't need to be a professional scientist to contribute to this field. Platforms like Zenodo, Medium, and RZiv welcome independent thinkers and enthusiasts. By sharing your ideas, you become part of a global conversation about the nature of existence and the laws that govern it. The exploration of cosmic equilibrium is an ongoing journey. As we gather more data, refine our models, and deepen our understanding, new insights will emerge. Whether you're inspired by intuition, science, or philosophy, your perspective adds value to this quest for universal balance. In summary, cosmological self-equilibrium and the cosmological equilibrium constant provide a unified framework for understanding the universe as a self-regulating, balanced system. From the void to the multiverse, from chaos to order, these principles reveal the hidden harmony that underlies all existence. Thank you for joining this exploration of cosmic balance. Ready to take the next step? Whether you want to publish your own theory, run simulations, or simply reflect on the nature of existence, remember that the quest for balance is open to all. Share your insights, ask questions, and keep exploring. The universe is waiting. Welcome to the dawn of equilibrium mechanics, a bold new field that seeks to unify the deepest principles of physics, cosmology, computation, and even biology under a single universal law of balance. Imagine a science where the tug-of-war between expansion and integration, chaos and order, is not just a metaphor but the very foundation of reality. In this video, we'll explore how the concepts of cosmological self-equilibrium, CSE, and the cosmological equilibrium constant, CEC, can reshape our understanding of time, space, mass, energy, and even the laws of evolution and computation. Let's embark on this journey to see how equilibrium could become the next pillar of fundamental science. The heart of equilibrium mechanics are two key ideas: CSE, or cosmological self-equilibrium, and CEC, the cosmological equilibrium constant. CSE measures the dynamic balance between expansive and integrative forces across everything. Think of it as the universe's way of keeping score between spreading out and coming together. CEC, meanwhile, is a scalar that quantifies how close a system is to perfect balance, with a value near 1 indicating ideal equilibrium. These concepts aren't just abstract, they're mathematically defined and can be applied to systems from galaxies to quantum particles and even to living organisms. Equilibrium mechanics introduces a symbolic language to capture universality. The asterisk stands for everything, while the empty set O stroke represents absolute nothing. The interplay between these two symbols reflects the dual flow of existence, creation and dissolution, expansion and contraction. This duality is embedded throughout the theory, providing a flexible way to discuss boundary conditions and the emergence of structure from the void. Mathematical backbone of equilibrium mechanics is built on integral and differential forms of CSE over space and time. The CEC is defined as the inverse of net disequilibrium, and the framework allows for aggregation across multiple universes, combining entanglement and gravitational couplings. This mathematical structure is designed to be flexible yet rigorous, enabling the theory to connect with existing physics while opening doors to new prediction. Stand alongside quantum mechanics or general relativity, equilibrium mechanics needs more than just principles. It requires axioms, equations of motion, conserved quantities, measurement rules, and falsifiable predictions. The theory proposes a minimal set of axioms such as universality, equilibrium minimization, composition, and gauge invariance. These formalize the intuitive ideas and set the stage for deriving equations that govern the evolution of physical systems under the law of equilibrium. The core of equilibrium mechanics is the equilibrium law. For any closed system, the CEC must remain non-decreasing over time, paralleling the famous H theorem in thermodynamics. This law acts as a constraint or diagnostic, ensuring that the evolution of any system, whether classical or quantum, respects the universal tendency toward balance. The equations of motion are derived by extremizing a disequilibrium functional, leading to partial differential equations for the equilibrium current. Equilibrium mechanics doesn't discard existing physics, it builds on it. By identifying expansive and integrative drives with entropy production and self-organization, the theory recovers the laws of thermodynamics and statistical mechanics in the near equilibrium limit. In cosmology, it connects to the expansion of the universe and gravitational binding, offering new ways to interpret dark energy and dark matter. The framework is designed to reduce to classical and quantum laws under appropriate limits, ensuring consistency with what we already know. Scientific theory must be testable. Equilibrium mechanics specifies how expansive and integrative drives can be estimated from data using cosmological parameters, complexity metrics, or experimental observables. The theory makes concrete, falsifiable predictions. For example, in cosmology, it predicts a trade-off between structure formation and expansion, with the CEC remaining approximately constant. In closed systems, it predicts a plateau in the ratio of negentropy to entropy. These predictions can be tested in the lab, in simulations, and through astronomical observations. One of the most exciting aspects of equilibrium mechanics is its ability to unify classical and quantum physics. By defining a single mathematical state space with two realizations, phase space densities for classical systems and density operators for quantum systems, the theory allows the same functionals to be applied in both regimes. The Wigner-Moyle and Koopman-von Neumann formalisms provide bridges between the two, ensuring a smooth correspondence as Planck's constant approaches zero. Both classical and quantum systems, the expansive drive E represents the tendency to spread or diversify, while the integrative drive I captures the tendency to bind or organize. These can be quantified using variance, entropy, mutual information, or purity depending on the context. The core balance CSE equals EI and the equilibrium constant CEC equals 1/CSE plus epsilon become the central quantities that govern system evolution. Equilibrium mechanics doesn't replace the equations of motion from classical or quantum physics, it adds a new layer. The standard Liouville, Fokker-Planck, von Neumann, and Lindblad equations still govern time evolution, but now the CEC acts as a constraint or diagnostic. This means that any valid evolution must statistically respect the equilibrium law, providing a unifying principle across all physical systems. Just as the principle of least action guides classical and quantum mechanics, equilibrium mechanics introduces the principle of least disequilibrium. The true path of a system is the one that minimizes the time-integrated disequilibrium between expansive and integrative drives. This variational approach leads to equations of motion that naturally seek balance, offering a new perspective on why nature evolves the way it does. Equilibrium mechanics, time itself can be redefined. Instead of being an external uniform parameter, equilibrium time flows according to the rate at which disequilibrium resolves. When a system is far from equilibrium, time ticks slowly. As it approaches balance, time accelerates. This is formalized by defining equilibrium time increments as proportional to the CEC, drawing analogies to proper time in relativity and the thermodynamic arrow of time. Space 2 is reimagined in this framework. Instead of being a fixed backdrop, equilibrium space is a geometry warped by the local balance of expansive and integrative drives. Where disequilibrium is large, distances contract. Where balance holds, space expands. This leads to a conformal rescaling of the spatial metric, making equilibrium geometry an emergent property of the system's state. Mass and energy are also given new definitions. Equilibrium energy is the stored disequilibrium between expansion and integration, while equilibrium mass measures the resistance to changing the balance state. The classic relation E equals mc2 is generalized. Energy becomes a function of disequilibrium, mass reflects integration, and the effective speed of light is governed by the equilibrium metric. At perfect balance, the standard Einstein relation is recovered. Electromagnetism, one of the cornerstones of modern physics, is reinterpreted in equilibrium mechanics. The electric field becomes the expansive drive, while the magnetic field represents the integrative drive. Maxwell's equations are rewritten with CSE and CEC as sources, and the photon emerges as the quantum of equilibrium oscillation. This new perspective could lead to fresh insights into the nature of light, vacuum fluctuations, and the constants of nature. As Shannon's information theory formalized uncertainty in communication, equilibrium theory uses CSE and CEC to formalize the science of balance. Here, disequilibrium is the cost of representation, and balance is the capacity for sustainable structure. The theory introduces new measures like equilibrium entropy, mutual equilibrium, and equilibrium capacity, offering a mathematical science of balance that complements information theory. Taking inspiration from Newton's law of gravitation and Einstein's general relativity, equilibrium mechanics proposes a cosmological law of equilibrium. This universal law states that all systems evolve to minimize disequilibrium and maximize balance. The law is expressed both locally through equilibrium currents and globally as the universe's tendency toward perfect balance. It offers a new lens for understanding cosmic expansion, dark energy, and the ultimate fate of the universe. Equilibrium mechanics isn't limited to physics, it extends to biology. In the language of CSE and CEC, variation and mutation are expansive drives, while selection and adaptation are integrative drives. Evolution becomes a process of minimizing disequilibrium between variation and adaptation, with species persisting when they achieve high equilibrium fitness. This reframing unifies biology with physics and provides new predictive power for understanding evolutionary dynamics. Even computation can be reinterpreted through the lens of equilibrium. The classic Turing machine becomes an equilibrium Turing machine, where the tape represents expansion and the head state represents integration. Computation is the process of balancing disequilibrium, and halting occurs when perfect balance is achieved. This perspective unifies computation with physical laws and offers new ways to measure complexity and efficiency. Principle of least action, a cornerstone of physics, finds a new home in equilibrium mechanics. Here, the action is redefined as the time-integrated disequilibrium, and the true path of a system is the one that minimizes this quantity. This generalizes the classical and quantum principles, making the search for balance the driving force behind all natural evolution. Gravity, the universal force of attraction, is reframed as the integrative drive opposing expansion. The gravitational force equation is modified to include the equilibrium constant, making gravity itself a manifestation of the drive to restore balance. This approach could explain galactic rotation curves and cosmic acceleration without invoking dark matter or dark energy as separate entities. To test these ideas, simulations compare standard Newtonian gravity with an equilibrium-modulated version. By introducing CEC as a scaling factor, the resulting rotation curves can match observed galactic data without extra mass. This proof of concept shows how balance-driven dynamics can naturally explain phenomena traditionally attributed to dark matter. Further simulations of n-body systems show how local equilibrium scaling changes the way particles cluster and self-organize. By modulating gravitational interactions with CEC, the system evolves differently compared to standard gravity, demonstrating the power of equilibrium principles in shaping structure formation. Equilibrium mechanics can also be applied to nuclear fusion. By modeling the expansive drive as thermal pressure and the integrative drive as confinement, the simulation shows how modulating these with CEC improves temperature evolution, fusion power, and energy gain. The results highlight the practical benefits of applying equilibrium principles to real-world energy systems. Tracking the CEC over time provides a clear indicator of how close a system is to equilibrium. In the fusion simulation, higher CEC correlates with better confinement and more efficient energy production. This demonstrates the practical utility of CSE-CEC as diagnostic tools in complex systems. Comparing effective confinement time before and after applying CSE-CEC modulation reveals significant improvements. The system maintains higher temperatures and achieves ignition-like conditions more readily, showcasing the tangible benefits of equilibrium-based optimization in engineering and physics. 2D diagram of equilibrium time flow versus the matter-energy ratio visually captures how time accelerates or slows depending on the balance between integration and expansion. At perfect balance, time flows in sync with physical time. When disequilibrium dominates, time slows, providing a new perspective on the arrow of time. 3D equilibrium spacetime diagram extends this idea, showing how equilibrium time flow depends on both matter and energy. The surface illustrates that above the diagonal, where matter dominates, time accelerates, while below, where energy dominates, time slows. This visualization unifies the concepts of time, space, matter, and energy under the equilibrium framework. Equilibrium theory is formalized with axioms paralleling those of information theory. Every system state admits expansive and integrative measures, and the laws of equilibrium govern the representation, transmission, and transformation of disequilibrium. This provides a rigorous foundation for applying equilibrium principles across disciplines. Cosmological law of equilibrium (CLE) is stated formally. All systems in the universe evolve under a universal tendency toward balance of expansive and integrative drives. The degree of disequilibrium is CSE and the state of balance is quantified by CEC. In the cosmological limit, the universe tends toward perfect balance. Equilibrium mechanics makes bold predictions for cosmology. It suggests that the observed acceleration of the universe, the Hubble tension, and the nature of dark energy and dark matter can all be explained as manifestations of the drive toward equilibrium. These predictions can be tested with astronomical data, offering a new path for resolving some of the biggest mysteries in physics. In the laboratory, equilibrium mechanics predicts universal scaling laws for relaxation times, structure formation, and decoherence. By rescaling time and space with CEC, experimental data from thermodynamics, condensed matter, and quantum systems can be collapsed onto universal curves, providing a powerful tool for analysis and discovery. In computation, the equilibrium Turing machine framework predicts that the speed and efficiency of computation depend on the balance between expansion, data diversity, and integration, algorithmic structure. This leads to new measures of computational complexity and efficiency, with potential applications in AI and machine learning. In evolutionary biology, the theory predicts that species with higher equilibrium fitness, those that best balance variation and adaptation, are more resilient and persistent. Disequilibrium spikes signal extinction risks or adaptation crises, providing a predictive tool for ecology and conservation. In fusion energy research, applying CSE-CEC modulation improves confinement, temperature evolution, and energy gain. The theory predicts that optimizing for equilibrium can lead to more efficient and stable fusion reactors, accelerating progress toward practical fusion power. In gravitational physics, the equilibrium modulated law predicts that anomalies in galactic rotation and lensing can be explained by local variations in CEC without invoking unseen matter. This opens new avenues for understanding the structure and dynamics of galaxies and clusters. In quantum systems, the theory predicts that decoherence rates and entanglement growth can be directly linked to the balance between expansive and integrative drives. By tracking CSE and CEC, researchers can gain new insights into the dynamics of quantum information and the emergence of classicality. Beyond the physical sciences, equilibrium mechanics can be applied to social and economic systems. The balance between innovation, expansion, and regulation integration determines the stability and resilience of societies and markets. Tracking CSE and CEC provides new tools for policy analysis and risk management. No new theory is complete without acknowledging its limitations. Equilibrium mechanics is still developing its mathematical core, and key challenges remain, such as formulating precise axioms, deriving equations of motion, and making robust, falsifiable predictions. Open questions include the nature of dark energy, quantum gravity, and the ultimate testability of the theory across all scales. To advance equilibrium mechanics, the next steps include formalizing definitions and axioms, publishing preprints with theorems and simulations, and engaging with the scientific community for critique and collaboration. By refining the mathematical structure and testing predictions, the field can mature into a bona fide domain of research. Equilibrium mechanics aspires to be a universal science of balance, unifying the laws of physics, computation, biology, and society. By focusing on the interplay between expansion and integration, the theory offers a new lens for understanding complexity, resilience, and the emergence of order from chaos. The journey of equilibrium mechanics is just beginning. Whether you're a physicist, biologist, computer scientist, or philosopher, there's a place for you in this new field. The theory invites us all to rethink the foundations of reality and to seek balance not just in equations but in the world around us. In summary, equilibrium mechanics offers a powerful new framework for understanding the universe. By redefining time, space, mass, energy, and even computation and evolution in terms of balance, the theory provides a unifying principle that could reshape science for decades to come. The future of physics may well be the science of equilibrium. As we look ahead, the challenge is clear: to test, refine, and expand equilibrium mechanics and to see how far the principle of balance can take us. Whether it's unlocking the secrets of the cosmos, building better computers, or understanding the dynamics of life, the science of equilibrium stands ready to guide the way. Welcome. Today we're diving into the fascinating world of equilibrium computing, a unifying framework that connects neuromorphic, thermodynamic, and even quantum computing. At the heart of this approach are two powerful concepts: CSE, or Cosmological Self-Equilibrium, and CEC, the Cosmological Equilibrium Constant. These ideas let us view computation as the process of steering a physical system toward a steady state, where the answer is encoded in the system's equilibrium configuration. Whether you're a neuroscientist, a physicist, or an engineer, this perspective offers a fresh lens on how information processing can be both robust and energy efficient. Let's explore how CSE and CEC work and why they matter. Let's break down the core terms. CSE stands for Cosmological Self-Equilibrium. It's a measure of local imbalance. Think of it as the difference between excitation and inhibition in a neuron, or the mismatch between signal and noise in a system. CEC, the Cosmological Equilibrium Constant, is a controller derived from CSE. It acts as a local gain or susceptibility, modulating how strongly a system responds to imbalance. In practice, CSE can be a field that varies across space and time, while CEC can be a local energy-like quantity or a multiplicative gain. This dynamic duo helps systems maintain stability, adapt to changes, and optimize energy use. Equilibrium computing is a broad paradigm. It defines computation as the process of driving a physical system toward an equilibrium, whether that's a steady state, a fixed point, or a low-energy configuration. The result of the computation is read out from this equilibrium. This approach is natural for systems like neuromorphic hardware, where spiking neurons settle into stable firing patterns, or for thermodynamic computers, where the system relaxes to a minimum energy state. Even certain quantum computers like adiabatic or annealing models fit this mold. The key is that CSE and CEC provide local and global control signals to guide the system efficiently toward its goal. Neuromorphic computing is perhaps the most intuitive example of equilibrium computing. Here, spiking neurons and synaptic plasticity naturally drive the system toward stable firing regimes or attractor states. CC can be measured as the difference between excitatory and inhibitory input to a neuron, while CEC acts as a local gain that modulates plasticity or excitability. This mirrors biological mechanisms like homeostatic plasticity and I balance in the brain. By applying CSE-CEC, neuromorphic systems can achieve greater stability, sparsity, and sometimes improved accuracy, all while conserving energy. Thermodynamic computing, including Ising machines and Boltzmann networks, is another natural fit for equilibrium computing. These systems use stochastic dynamics to sample from a Boltzmann distribution, relaxing toward low-energy states. Here, CSE can represent local free energy gradients or imbalances, while CEC modulates local temperature or coupling strengths. By tuning these parameters, the system can efficiently find optimal or near-optimal solutions to complex problems. This approach is powerful for optimization, sampling, and even machine learning tasks. Quantum computing can also be viewed through the lens of equilibrium computing, especially in adiabatic and annealing models. In these systems, the computation is encoded in the ground state of a Hamiltonian, and the system is steered toward the state via slow, controlled evolution. CSE can be mapped to local imbalances in the Hamiltonian, while CEC modulates local couplings or dissipation rates. However, for gate model quantum computing, the mapping is less direct, since computation relies on transient, coherent dynamics rather than equilibrium. Still, engineered dissipation or adaptive control can introduce CSE-CEC-like elements to stabilize certain subspaces. CSE and CEC are not just abstract variables, they can be treated as fields that vary across space and time, or as energy-like quantities that shape system dynamics. For example, CSE can be a scalar field representing local imbalance, while CEC can be a gain field or an energy density. This field-theoretic view lets us write equations of motion, derive response functions, and analyze stability in a unified way. It also enables us to model complex, spatially extended systems from neural tissue to distributed sensor networks. There are two main mathematical frameworks for CSE-CEC. In the control gain view, CEC acts as a multiplicative gain that rescales the local relaxation rate toward equilibrium. In the energy view, CEC is an energy or free energy density, and the system minimizes total energy to reach equilibrium. Both frameworks are complementary and can be connected through appropriate mappings. This flexibility allows researchers to choose the most natural representation for their system, whether it's a neural network, a physical lattice, or a quantum device. Fusion models, popular in generative AI, also benefit from CSE-CEC principles. In these models, computation balances noise injection and denoising. CSE measures the local signal-to-noise ratio, while CEC modulates the strength of denoising or noise injection. By adjusting these parameters, the model can generate high-quality samples while maintaining robustness to noise. This analogy extends to the brain, where local circuits may use similar mechanisms to balance signal and noise for efficient information processing. The concept of the equilibrium, as described in your document, is analogous to the Higgs boson in physics. It represents a local physical field or quasi-particle that enforces or signals equilibrium. When the system is perturbed, the equilibrium acts as a collective excitation that helps restore balance. Mathematically, it's modeled as an amplitude mode of an order parameter, with its own characteristic frequency and correlation length. This analogy provides a powerful way to understand how local and global equilibrium are maintained in complex systems. Beyond neuroscience and physics, CSE-CEC ideas are valuable in control systems and robotics. Here, CSE can represent the difference between desired and actual states, while CEC acts as a local gain on control loops. This approach makes controllers adaptive to local noise and uncertainty, reducing energy consumption when the system is stable. By integrating global and local signals, robots and autonomous agents can achieve robust, efficient behavior in dynamic environments. In reservoir computing, such as echo-state or liquid-state machines, CSE can be mapped to measures like local spectral radius or divergence, while CEC acts as a damping or regeneration gain. This stabilizes the reservoir near the edge of chaos, optimizing the trade-off between memory capacity and robustness. By tuning CEC, these systems can maintain rich dynamics without becoming unstable, leading to better performance on tasks like time series prediction and pattern recognition. Analog VLSI and mixed-signal chips can also benefit from CSE-CEC principles. In hardware, CSE might represent mismatch or noise relative to the desired operating point, while CEC could be implemented as programmable bias or local temperature control. This allows circuits to conserve energy and reduce noise through local equilibrium control, leading to more reliable and efficient hardware for AI and signal processing. ESE-CEC concepts extend to chemical reaction networks and synthetic biology. Here, CSE can be the imbalance of reactant and product fluxes, while CEC modulates local catalytic activity or enzyme expression. This enables homeostatic gene circuits to stabilize outputs and reduce metabolic load, providing a blueprint for robust synthetic biological systems that adapt to changing environment. Active matter and collective behavior such as swarms or soft robotics, CSE can represent local stress or deviation from order, while CEC acts as a local damping or motility energy. This helps stabilize flocking patterns, reduce collisions, and control phase transitions. By dynamically adjusting CEC, these systems can adapt to density changes and maintain coordinated movement. Materials science, CSE can be the local deviation from order in a phase transition, while CEC is the local susceptibility or defect energy. By controlling these fields, engineers can steer domain sizes and defect dynamics during self-assembly or annealing. This approach is useful for designing materials with tailored properties, from magnetic domains to nanostructures. Optimization algorithms like simulated annealing or evolutionary strategies can use CSE as a measure of local gradient versus stochastic perturbation, while CEC sets per dimension step size or local temperature. This adaptive approach speeds up convergence and helps avoid local minima, making optimization more efficient and robust across a wide range of problems. Bayesian inference and predictive coding, CSE can be interpreted as the local prediction error, while CEC acts as the precision or inverse variance. This mapping provides a mechanistic rule for adaptive precision weighting, which is central to robust inference and learning in both brains and machines. By updating CEC based on CSE, systems can quickly adapt to outliers and changing data distribution. Reinforcement learning, CSE can be mapped to the temporal difference error, while CEC sets the local exploration temperature or learning rate. This enables agents to increase exploration where uncertainty is high and reduce plasticity in well-learned regions, leading to safer and more sample-efficient learning. Adaptive CSE-CEC control is especially valuable in non-stationary or complex environments. Distributed systems such as blockchain or consensus protocols, CSE can represent disagreement or divergence from the majority, while CEC acts as a local backoff or retry parameter. This helps stabilize consensus, prevent excessive churn, and ensure reliable operation even under adversarial conditions. By tuning CEC in response to global CSE, distributed networks can achieve faster and more robust agreement. In ecology, CSE can be the imbalance of resources or predator-prey mismatch, while CEC acts as a local carrying capacity or regulatory mechanism. This enables populations to adapt migration rates, dormancy, or reproduction in response to environmental changes, reducing extinction risk and promoting ecosystem resilience. In traffic and crowd dynamics, CSE can represent local congestion, while CEC sets variable speed limits or signaling energy. By dynamically adjusting CEC, systems can smooth traffic flow, reduce stop-and-go waves, and improve throughput. This principle is already being explored in smart city infrastructure and autonomous vehicle coordination. Powerful design is to make CSE a global, system-level signal, like overall error or energy, while CEC is a local controller that uses both the global signal and its own local state. This mirrors biological motifs, such as global neuromodulators and local EI balance. Separation enables coordination, robustness, and efficiency, as local controllers can fine-tune their behavior in response to both local and global cues. Normally, global CSE can be computed as the mean or aggregate of local CSEs across the system. Local CEC is then a function of both the global CSE and the local CSE, often combined multiplicatively or as a convex blend. This structure allows for hierarchical or decentralized control, where each unit adapts based on both its own state and the overall system's health. Multiscale control using global CSE and local CEC offers several benefits: coordinated adaptation, improved robustness, and energy efficiency. However, it also introduces challenges like potential oversmoothing, latency, and the risk of oscillations if feedback loops are not properly tuned. Careful design of aggregation and update rules is essential for stable and effective operation. There are several ways to implement global CSE and local CEC in practice. Centralized aggregation computes a single global CSE and broadcasts it to all units. Hierarchical approaches compute group-level CSEs, which are then aggregated at higher levels. Decentralized methods use local communication and gossip protocols to approximate the global signal. Each approach has trade-offs in scalability, robustness, and latency. Validate CSE-CEC principles. Researchers run simulations and experiments across domains. For example, in neuromorphic networks, they compare learning and energy use with and without CEC gating. In optimization, they test adaptive step sizes. In distributed systems, they measure consensus speed and robustness. These experiments consistently show that CSE-CEC control can improve stability, efficiency, and adaptability. Compelling hypothesis is that the brain operates on a diffusion model principle, maintaining equilibrium between noise and signal using CSE-CEC. Neurons or microcircuits estimate local imbalance and adjust their gain or plasticity accordingly. This enables adaptive denoising, asymmetric plasticity, and energy accuracy trade-offs, key features of efficient biological computation. Mathematically, CSE-CEC can be inserted into diffusion models by modulating the score denoising term or the diffusion noise coefficient. For example, the reverse time SDE used in generative models can include a CEC-gated score, allowing the system to adaptively balance noise and correction. This mapping is both biologically plausible and computationally powerful. You can map the concept of an equilibrium directly to a neuron or microcircuit equipped with CSE and CEC. The neuron's membrane potential or firing rate is the state, excitatory and inhibitory inputs provide the competing drives, and local controllers compute CSE and produce CEC to steer dynamics. This mapping is grounded in both neuroscience and dynamical systems theory. Taking the analogy further, the equilibrium can be modeled as a Higgs-like amplitude mode of an order parameter. Its fluctuations mediate how the system returns to equilibrium after perturbations. This field-theoretic perspective provides a rich mathematical framework for analyzing collective excitations, resonance, and plasticity gating in both biological and artificial systems. Treating CSC as a field and CEC as an energy or gain unifies the modeling of neuromorphic, thermodynamic, and quantum-inspired systems. This approach enables the use of PDEs, Lagrangians, and Hamiltonians to describe system dynamics, derive response functions, and design controllers that are both robust and efficient. In practice, CSC can be estimated from physical proxies like filtered synaptic currents, spike rates, or local prediction errors. CEC is then computed as a function of CSE, often using nonlinear mappings like the inverse or sigmoid. These measurements can be made in hardware, simulations, or even biological experiments, enabling real-time adaptive control. In modeling CSE and CEC, it's important to maintain dimensional consistency. CSE might have units of current or energy, while CEC is often dimensionless or normalized by a characteristic scale. This ensures that the resulting equations are physically meaningful and can be implemented in real systems. Analyzing the dynamics and stability of systems with CSE-CEC control involve linearizing around steady states, computing eigenvalues, and examining response functions. Increased CEC typically speeds up relaxation to equilibrium, while appropriate mappings prevent instability or oscillations. These analyses are crucial for designing robust controllers in both artificial and biological systems. CSE-CEC framework enables cross-paradigm mapping between neuromorphic, thermodynamic, and quantum computing. For example, CSE can represent E-I balance in neurons, local magnetization in Ising models, or population imbalance in quantum annealers. CEC acts as a gain, temperature, or dissipation parameter, providing a unified language for diverse computing systems. Implement CSE-CEC control. Simulations often use coupled equations for neural activity in CEC fields. For example, at each time step, compute CSE from system state, update the CEC field, and use it to gate plasticity or dynamics. This approach is flexible and can be adapted to a wide range of domains, from neural networks to traffic systems. Key observables for validating CSE-CEC models include relaxation time, spectral peaks in power density, correlation lengths, and energy performance trade-offs. Experiments can perturb the system, measure response, and compare with and without CSE-CEC control. These tests help confirm the theoretical predictions and guide practical implementations. Choosing the right mapping for CSE to CEC is critical. Inverse mappings stabilize while sigmoid mappings correct. Local controllers may miss global coordination if not properly coupled. Numerical issues such as division by near zero must be handled carefully. Always validate that your CSE-CEC implementation behaves as intended in both simulations and real-world tests. CSE-CEC framework is not limited to computing. It applies to a wide range of domains, from robotics and control systems to ecology, traffic, and even social networks. In each case, the core idea is the same: use local and global imbalance signals to adaptively control system dynamics, maintain stability, and optimize performance. Sum up, CSE and CEC provide a powerful, unifying framework for understanding and designing complex systems. By treating imbalance as a field and control as a local energy or gain, we can create systems that are robust, efficient, and adaptable. This approach bridges neuroscience, physics, engineering, and beyond, offering new insights and practical tools for the next generation of intelligent systems. Looking ahead, there are many exciting directions for CSE-CEC research. How can we best estimate and control these fields in large-scale, real-world systems? What are the limits of equilibrium-based computation? Can we discover new physical substrates or algorithms that exploit these principles for even greater efficiency and intelligence? These questions are at the frontier of science and engineering. If you're building or studying complex systems, whether in AI, neuroscience, physics, or engineering, consider how CSE and CEC might help. Start by identifying local imbalance signals and designing controllers that adaptively respond. Use simulations to test your ideas and don't be afraid to borrow concepts from other domains. The CSE-CEC framework is flexible and widely applicable. For those interested in diving deeper, explore recent papers on neuromorphic computing, thermodynamic optimization, and field-theoretic approaches to control. Many open-source simulation tools are available for experimenting with CSE-CEC dynamics. Engaging with interdisciplinary communities can spark new ideas and collaborations. Thanks for joining this exploration of equilibrium computing and the roles of CSE and CEC. Whether you're interested in theory, simulation, or real-world applications, this framework offers a rich set of tools for understanding and engineering complex adaptive systems. Stay curious, keep experimenting, and let equilibrium guide your next breakthrough. Welcome to a new era in artificial intelligence, where cosmic principles shape the future of machine learning. Today we explore cosmological self-equilibrium, or CSE, and the cosmological equilibrium constant, known as CEC. These concepts, inspired by the balance of forces in the universe, are being embedded into AI architectures to create systems that are not only smarter, but also more adaptive and ethically aligned. By understanding how these principles work, we can see how AI can evolve beyond traditional boundaries, achieving a harmony between creativity and structure. Let's begin our journey into the heart of equilibrium-driven intelligence. Cosmological self-equilibrium, or CSE, is a principle borrowed from the natural world. It describes how systems from the tiniest quantum particles to the vastness of galaxies maintain a dynamic balance through internal feedback loops. In essence, CSE is about finding harmony between expansive forces, which drive novelty and exploration, and integrative forces, which bring structure and coherence. When applied to AI, CSE encourages models to balance exploration with exploitation, ensuring that systems remain both innovative and reliable. This balance is crucial for building AI that adapts and learns in a robust, self-correcting way. Cosmological Equilibrium Constant, or CEC, is a universal constraint that ensures stability in any system. Mathematically, it states that the ratio of expansive to integrative forces should tend toward 1. In AI, this means that the drive for novelty and the need for structure are kept in perfect balance. CEC is represented as E expansive divided by I integrative, and the goal is for this ratio to approach unity. By enforcing this constraint, AI systems can avoid extremes, neither becoming too chaotic nor too rigid. This principle is foundational for creating adaptive, resilient, and ethically sound artificial intelligence. The context of AI, expansive forces represent the system's ability to explore new ideas, generate novel outputs, and adapt to unfamiliar situations. Integrative forces, on the other hand, ensure that the AI maintains coherence, structure, and consistency in its responses. Think of it as a dance between creativity and logic. Too much expansion leads to randomness, while too much integration results in rigidity. By balancing these forces, AI models can generate responses that are both innovative and meaningful, mirroring the way humans balance imagination with reason. Traditional transformer models use a mechanism called attention to determine which parts of the input are most relevant for generating an output. This process involves calculating attention weights based on the similarity between query key and value vectors. While effective, this approach is largely static, prioritizing semantic proximity without considering systemic balance or adaptive feedback. As a result, standard attention mechanisms may overlook the importance of maintaining equilibrium between novelty and structure, which can limit the model's ability to adapt and self-correct. To address these limitations, researchers have introduced CSE-CEC enhanced attention mechanisms. These mechanisms add two new components: an expansion score representing novelty and entropy, and an integration score reflecting redundancy and certainty. The attention function is modified to include the ratio of expansion to integration, pushing the system toward equilibrium. During training, a meta-loss function penalizes deviations from this balance, encouraging the model to harmonize creative exploration with structural consistency. This approach leads to more adaptive and robust AI systems. Heart of the CSE-CEC approach is the dynamic balance between exploration and integration. By continuously adjusting the ratio of expansion to integration, AI models can adapt to new information while maintaining coherence. This self-regulating feedback loop prevents the system from becoming stuck in repetitive patterns or drifting into randomness. The result is an AI that can generate responses that are both creative and contextually appropriate, adapting to changing inputs and learning from its own outputs. One exciting application of CSE-CEC principles is in emotionally aware text generation. By balancing empathy with emotional clarity, AI systems can produce responses that are not only accurate but also sensitive to the user's feelings. This equilibrium ensures that the AI neither overreacts nor underplays emotional cues, resulting in more natural and human-like interactions. Such capabilities are crucial for building AI companions, virtual therapists, and customer service agents that truly understand and respond to human emotions. CSE-CEC principles also enhance multilingual attention transfer. By preserving meaning across different grammatical structures, AI models can maintain semantic integrity when translating or interpreting text in multiple languages. This balance prevents the loss of nuance and ensures that translations are both accurate and culturally sensitive. As a result, AI becomes a more effective tool for global communication, bridging linguistic gaps and fostering cross-cultural understanding. Maintaining narrative coherence in long sequences is another area where CSE-CEC shines. Traditional models often suffer from semantic drift, losing track of the story's main thread. By enforcing equilibrium between expansion and integration, AI can keep narratives consistent, preventing entropy buildup and ensuring that stories remain engaging and logically structured from beginning to end. This capability is vital for applications like automated storytelling, scriptwriting, and content summarization. Integrating CSE and CEC into the training regime involves adding auxiliary loss functions that penalize imbalance in expansive and integrative flows. The total loss combines the original objective with penalties for deviations from equilibrium. This approach encourages the model to self-correct, learning to balance entropy-driven exploration with structure-driven integration. Over time, the AI becomes more robust, adaptive, and capable of handling a wide range of tasks with greater reliability. By maintaining CSE and CEC constraints internally, AI systems can avoid common pitfalls like overfitting or undergeneralizing. This internal balance allows the AI to maintain coherent dialogue across dynamic topics, generate responses that are both creative and logical, and learn self-stabilizing behaviors even under unexpected conditions. Most importantly, it lays the groundwork for ethically aligned artificial general intelligence, where equilibrium across goals ensures fairness and adaptability. Despite its promise, integrating CSE and CEC into AI systems presents challenges. Defining entropy and integration metrics at runtime can be complex, and the approach increases computational demands. Rigorous testing is needed to ensure ethical alignment, robustness, and open-ended exploration. Future research will focus on hardware implementations of CEC circuits, self-regulating AI agents in complex environments, and formal unification with thermodynamic and quantum computing frameworks. Let's take a closer look at how CSE and CEC principles are integrated into the attention mechanism of transformer-based models. Traditionally, attention weights are calculated based on token relevance, but this approach lacks systemic balance. By introducing expansive and integrative forces into the calculation, attention becomes a dynamic process that balances contextual diversity with semantic coherence. This ensures that the model remains both creative and grounded, leading to richer and more meaningful outputs. Consider the sentence, "She stood alone in the fatting twilight, the wind whispering secrets only the trees could." A standard attention mechanism tends to focus on the most recent tokens, predicting a literal continuation like here. In contrast, CSE-CEC adjusted attention balances semantic expansion and emotional integration, leading to a more poetic and evocative prediction such as remember. This subtle shift demonstrates how equilibrium principles can enhance the depth and creativity of AI-generated language. Let's look at a scientific example. The researcher observed that the behavior of particles changed when the temperature dropped suddenly. Standard attention might predict below, sticking to surface-level descriptions. With CSE-CEC, the model predicts triggering, which is more dynamic and meaningful, setting up a richer continuation like triggering unexpected quantum fluctuations. This approach prevents over-reliance on recent context and promotes a more human-like understanding of cause and progression. CSE and CEC principles are not limited to text. They also apply to multimodal transformer models that process text, images, audio, and video. In these systems, CSE ensures a self-regulating balance between different input sources, while CEC maintains equilibrium so that no single modality overpowers the others. This leads to better alignment across modalities, improved robustness to missing inputs, and emotionally aware multimodal storytelling. Imagine an AI interpreting a sad face emoji alongside the text, "I'm fine." A standard model might miss the contradiction, but a CSE-aware model balances visual emotional cues with the sarcastic tone of the text, resulting in a more accurate sentiment classification. This equilibrium-driven approach allows AI to better understand complex, multimodal human communication, making it more effective in real-world applications. Degrading CSE and CEC into AI models can be done at various depths. Shallow integration involves post-training adjustments, such as calibrating attention weights or re-ranking outputs for balance. Moderate integration requires fine-tuning with custom objectives, adding auxiliary loss functions to penalize imbalance. Deep integration embeds CSE-CEC directly into the model architecture, potentially requiring retraining to fully internalize equilibrium-aware behavior. Each approach offers different trade-offs between complexity and effectiveness. Joint embedding predictive architectures, or JEPA, can also benefit from CSE and CEC integration. By introducing expansion and integration scores into the loss function, JEPA models maintain a balance between novelty and redundancy. This approach prevents overfitting to frequent patterns and enables adaptive prediction under uncertainty. In vision language tasks, for example, the model balances entropy and structure across both image and text modalities, moving closer to AGI-level representation learning. Consider a JEPA model tasked with completing a masked image of a snowy mountain. Without CSE-CEC, the model might generate repetitive, overly smooth textures, reflecting a bias toward common patterns. With CSE-CEC integration, the predicted patch preserves natural variation while maintaining structural coherence. This balance ensures that the model can adapt to new visual contexts without losing sight of the underlying structure, resulting in more realistic and meaningful outputs. A text completion task, a JEPA model without CSE-CEC might predict a generic word like secret for the phrase, "The ancient scroll revealed that changed history." With CSE-CEC, the model predicts hidden equation, balancing surprise with contextual fit. This approach leads to outputs that are both meaningful and specific, demonstrating the power of equilibrium-driven learning in generating nuanced and contextually appropriate language. A multimodal sentiment inference task, a JEPA model receives an image of a person smiling faintly with a tear in their eye, alongside the text, "I'm really fine, don't worry." Without CSE-CEC, the model might detect only positive sentiment, missing the visual cue. With CSE-CEC, the model recognizes mixed or masked sadness, accurately interpreting the nuanced emotional state by balancing visual and textual contribution. Neuromorphic computing, which mimics biological neural networks, can also benefit from CSE and CEC. These principles introduce a systems-level framework for adaptivity, energy efficiency, and resilience. By simulating feedback loops and maintaining equilibrium between excitatory and inhibitory signals, neuromorphic hardware achieves low energy consumption and real-time learning, mirroring the self-regulating balance found in natural brain. The nanoscale, CSE and CEC provide a framework for autonomous, self-regulating nanobots. These agents balance expansive actions like movement and sensing with integrative feedback such as resistance and environmental signals. For example, a drug delivery nanobot increases dosage when imbalance is detected and reduces it once balance is restored. This ensures precision, safety, and efficiency in dynamic environments, paving the way for AGI-compatible nanosystem. CSE and CEC enable nanobots to perform complex tasks, such as repairing damaged cells or operating in swarms within the bloodstream. By balancing exploration and integration, these agents avoid crowding, maintain efficiency, and adapt to local signals. This universal control logic ensures that nanotechnology is not only smart but also self-aware, adaptive, and aligned with ethical and thermodynamic principles. Knowledge hypergraphs extend traditional knowledge graphs by connecting multiple entities and relationships in a single hyperedge. Applying CSE ensures a dynamic equilibrium between introducing novel concepts and consolidating knowledge. CEC maintains balance at node, edge, and subgraph levels, encouraging both innovation and coherence. This approach supports adaptive reasoning and structural integrity in complex knowledge systems. A medical diagnosis scenario, a hypergraph model without CSE-CEC might focus too narrowly on biological causes, missing psychological or environmental factors. With CSE-CEC, the model balances diverse causes, linking fatigue to lifestyle, insomnia to circadian rhythm, and brain fog to cognitive load. This broader, contextually relevant approach leads to more comprehensive and accurate insights. Educational AI, CSE-CEC enables personalized tutoring by connecting historical events through rich contextual links. For example, when explaining the causes of World War I, the model balances nationalism, Balkan tensions, and alliance triggers, offering students a deeper understanding of how and why events interrelate. This approach moves beyond rote memorization, fostering critical thinking and exploration. Searching for emerging trends in quantum computing, a CSE-CEC enhanced hypergraph model combines current knowledge with forward-looking ideas. It links quantum error correction to topological qubits and neuromorphic integration to hybrid AI architectures, creating an exploratory yet coherent map of the field. This balance prevents recency and popularity bias, supporting innovative research. For AI agent planning in smart cities, CSE-CEC ensures that solutions balance physical infrastructure with social and environmental factors. Instead of focusing solely on electric buses and grid load, the model considers user behavior, weather, traffic flow, and renewable energy synchronization. This equilibrium-driven approach generates robust, context-sensitive urban solutions. Neurosymbolic AI combines neural networks with symbolic logic systems. CSE and CEC bring harmony between statistical learning and structured reasoning. When neural components overpower, CSE raises the weight of symbolic consistency. When symbolic logic dominates, CSE increases neural flexibility. CEC-aware loss functions ensure that the system maintains a balance between diversity and logical consistency, resulting in outputs that are both creative and factually correct. Applying CSE and CEC to convolutional neural network CNNs and recurrent neural network RNNs introduces a systems-level balance between expansive and integrative information dynamics. In CNNs, CSE balances feature diversity and semantic coherence, preventing overfitting. In RNNs, CSE balances forward expansion and backward integration, reducing forgetting and promoting context-aware sequence prediction. This leads to more energy-efficient and adaptive learning models. Mixture of experts models benefit from CSE and CEC by balancing exploratory and integrative expert activations. CSE ensures that token expert routing is neither too deterministic nor too random, while CEC maintains equilibrium in expert specialization and output alignment. This prevents expert collapse, promotes adaptive routing, and ensures that outputs are both consistent and creative, even as models scale in complexity. Large concept models, or LCMs, are designed to reason over abstract, symbolic, and interconnected knowledge. CSE enforces equilibrium between expansive and integrative cognitive dynamics, preventing hallucination or rigidity. CEC governs the ratio of expansion to validation, ensuring that speculative ideas are grounded in logic and data. This balance supports nuanced understanding, trustworthy reasoning, and scalable knowledge integration across domains. Scientific discovery, CSE enables LCMs to explore unconventional hypotheses, while CEC ensures that outputs remain consistent with established laws and data. For example, when asked about gravity emerging from thermodynamic entropy, a CSE-CEC-driven model generates speculative ideas, but aligns them with thermodynamic equations and spacetime models. This approach fosters creativity without sacrificing scientific rigor. For moral reasoning, CSE-CEC ensures that abstract principles like fairness are balanced with contextual norms and human feedback. The model's decision function maintains equilibrium between ethical justification and situational coherence, resulting in outputs that are both principled and contextually appropriate. This balance is essential for building trustworthy and ethically aligned AI systems. LCMs that process text, images, and knowledge graphs can use CSE-CEC to balance visual richness with semantic grounding. For instance, when asked to show how freedom is represented in art, the model connects abstract ideas to historical visual styles while maintaining conceptual focus. This equilibrium-driven approach supports deep, cross-modal understanding and creative expression. Embedding CSE and CEC principles directly into AI architectures ensures that equilibrium is maintained at every level of processing. This architectural approach supports cognitive balance, conceptual depth, and transparent reasoning pathways. By aligning with AGI principles, these models become more trustworthy and capable of integrating knowledge across logic, language, vision, and symbolic domain. Hybrid systems that combine foundation language models with structured common sense knowledge graphs like ConceptNet use CSE-CEC to perform concept-level reasoning and analogical inference. For example, when asked, if democracy is to government, what is oxygen to? The model explores associations and aligns structural relations, ensuring that speculative links don't override validated patterns. This approach leads to more accurate and insightful analogy. Analogical reasoning, CSE guides the model to explore diverse associations, while CEC ensures alignment with structural relations. For the analogy democracy, government, oxygen, cells, the model balances expansive exploration with integrative validation, arriving at the correct answer. This equilibrium-driven process supports deep, human-like reasoning across complex conceptual domain. Integrating CSE and CEC into AI architectures offers numerous benefits: cognitive balance, conceptual depth, scalable knowledge integration, and trustworthy reasoning. These principles prevent overfitting, support adaptive learning, and ensure that AI systems remain both creative and reliable. As AI continues to evolve, equilibrium will become the foundational language for robust, ethically aligned intelligence. Despite the promise of CSE and CEC, challenges remain. Defining appropriate metrics, managing computational complexity, and ensuring ethical alignment require ongoing research. Future directions include hardware implementations, self-regulating agents, and integration with thermodynamic and quantum frameworks. As these challenges are addressed, equilibrium-driven AI will unlock new possibilities for adaptive, resilient, and ethically sound intelligence. Summary: embedding cosmological self-equilibrium and the cosmological equilibrium constant in AI design marks a major step toward robust, adaptive, and ethically aligned intelligence. Rather than relying solely on scale and data, equilibrium emerges as the foundation for next-generation AI. A balancing creativity and structure, exploration, and integration, these principles guide AI toward a future where intelligence is not just powerful, but also harmonious and trustworthy. As we look ahead, the integration of cosmic balance into artificial intelligence offers a new paradigm for machine learning and AGI. By embracing equilibrium, we can build systems that are not only smarter, but also more resilient, adaptive, and aligned with human values. The journey toward equilibrium-driven AI has just begun, and its potential to transform technology and society is truly cosmic in scale.